On page 209, there is problem number 3, the Batman problem. It says Batman, whose mass, I forgot to put that, mass is 80 kilograms, is dangling on a free end of a 12-meter rope. So here's Batman, here's a 12-meter rope. That's him dangling. It's supposed to be a tree right here. The other end, which is fixed to a tree limb. There it is. All right, he is able to get the rope in motion, as only Batman knows how, eventually getting it to swing enough that it can reach a ledge where the rope makes a 60-degree angle with the vertical. So here's like a building, and here's a ledge on the building, and he swings it up so that this is a 60-degree angle. Okay? And he wants to get this person. Now this person is telling him that if he just takes the elevator, he'll get the same answer. Okay? And that's hopefully what we're going to see here in a minute. So we want to know, what we want to know is how much work was done by the gravitational force on Batman in this maneuver. So we have an equation for work. And by the way, the force is, well, let's start with the most complicated, advanced one. F dot dr, or ds. Sometimes dr, sometimes ds. But in this case, if I draw a picture of, if I look at Batman, I want the force of gravity is just mg acting on Batman like that, and that force is a constant force. So this force is constant, and so we don't need to worry about the integral sign. If whenever you have a problem where the force is constant as you move through your displacement, you don't need to integrate. It'll just be F dot delta R. And now, if I look at this force, it's going to be mg, and that's going to be in the negative j hat direction. So I don't have to put negative 9.8 there, right? Because I put it in the negative j hat direction. Let's define an axis system here. Let's just say that x is positive. We don't even need x, and y up is positive y. Now I'm going to dot that with whatever delta r is. So Batman's going to swing up like this. So he's going to move a certain displacement in the x direction. I'll just call that delta x in the I hat direction. So wait, all of this is the force dotted with the displacement. And this is going to be delta y in the j hat direction. Okay. Now does everybody see what I did there? So here's Batman right here. Batman's going to end up on this ledge. That is my delta r. And delta r has an x component and a y component. Remember, work is done when a force is applied through a displacement, and it obeys this dot product. So I can now start plugging stuff in. Well, it's negative j dot, well, what is j dot I? J dot I is 0. So in other words, gravity's not going to do any work on Batman if he moves horizontally, because that motion is perpendicular to that force. So there's no work done by that force. But he is going to go up, and so gravity will be doing work there. So that's going to be mg delta y. Now what is, we have a negative here from here, and what is j dot j? Is 1 with no direction associated with it. This is a scalar. Work is a scalar. Now, what do I need to do now? Do I know what the mass is? Yes. Do I know what g is? Yes. Do I know what delta y is? No, but I can figure it out. I know what this length is here. It's 12 meters. Let me redraw the the triangle there. Here's 12 meters. Here's 60 degrees. And this is going to be, this is just going to kind of swing up like this. So this is 12 meters here. So this is my delta y from here up to here. So I need to figure out what that length is. So what I can do is take this length, that 12 meter length, and subtract this length from it. So I need to know what that length is. But 12 meters is the hypotenuse of this right triangle. See this right triangle right here? And here's what, you got to pop in that geometry you learned. We want this length, which, and I made it look like it's 12 meters, but it's obviously less than 12 meters. So what is it? Well, it's 12 meters times the cosine of 60 degrees. Now, what is the cosine of 60? It's 1/2. So 12 times 1/2, that's going to be 6 meters. So if this is 6 meters, then I went up 6 meters. I didn't draw this very well. So this went up 6 meters. So my delta y was 6 meters. So negative, what was it? 80 kilograms. Times 9.8. We can use meters per second squared or newtons per kilogram, whatever you prefer. Times delta y, which we got as being 6 meters. Do you see where I got the 6 meters here? Yes. Okay, let's just go over that again. This is 12 meters. This is a 60-degree angle, even though I didn't draw it as one. So this adjacent leg will be half as long as the hypotenuse. So this will be also half as long as the hypotenuse from here to here. And so now I just need to multiply all that. 80 times 9.8 times 6 equals 4,000. Wait, is that right? Yeah, 4,704, it's negative, joules. Is that right? Is that the answer in the back? Wow. So the work done by gravity was negative 4,704 joules. So gravity did negative work. Now look, that makes sense because Batman, by swinging his bat legs back and forth, he's taking chemical potential energy that's in his body, and when you're on a swing and you get it swinging back and forth, you're taking, you're trying to give yourself some kinetic energy. Well, as he swings up, as Batman swings up, what is gravity doing? Slowing you down, taking that energy away. Okay, whenever, look, and here's another way of thinking about it. Whenever the force of gravity is down, his displacement was up. Whenever the force and displacement are in opposite direction, negative work is being done. So in other words, that the work that's being done is trying to slow the object down, trying to take its energy away. It's, in this case, kinetic energy. Of course, the kinetic energy is becoming what will be called in the next chapter gravitational potential energy. So this problem is kind of anticipating what we're about to do in Unit 4. Okay? So, bottom line is that in calculating the work done by a force, I started with the very basic equation. And then I start breaking it down. Oh, the force is constant. I don't need to worry about the integral. Okay, what is the force in IJK form? What is the displacement? Split up the displacement into its components. And then, then you have to look at the geometry to figure out specific things. Like we didn't know what delta y was, so we had to figure it out here and then plug it in and get your answer. Any questions? That is all.